Could the remains of a dead star become stranger than a black hole? At first, the question seems almost impossible. Black holes are the places where gravity becomes so intense that not even light can escape, where space and time bend toward a hidden boundary, and where our best theories begin to strain against one another. Yet a black hole may not be the most complicated object a dying star can leave behind. Somewhere between ordinary matter and complete gravitational collapse, nature may create objects with surfaces, internal layers, superfluid oceans, magnetic fields trillions of times stronger than Earth's, and perhaps forms of matter that have never existed anywhere else since the earliest moments of the universe. Before we begin, what time is it where you are? And where in the world are you listening from tonight? Wherever you may be, imagine the sky above you growing darker and quieter until only a few distant stars remain. Each of those points of light is a temporary balance. Gravity pulls inward, trying to compress the star, while heat and pressure from nuclear reactions push outward. For millions or billions of years, these opposing tendencies remain almost perfectly matched. A star shines because it is holding itself together and holding itself apart at the same time. Its calm appearance is the visible result of a struggle that never truly stops. To understand what happens when that balance ends, it helps to begin with the simplest truth about stars. They are not eternal fires. They are vast spheres of gas, mostly hydrogen and helium, held together by their own gravity. Deep in the core, hydrogen nuclei collide and fuse, forming helium and releasing energy. That energy slowly works its way outward, warming the star and supporting its enormous weight. The process can continue for a very long time, especially in smaller stars that consume their fuel gently. But every star eventually changes. Its core composition shifts, its temperature rises, and the reactions that once sustained it become less effective or move on to heavier elements. The exact manner of death depends mostly on mass. A star like the Sun will never become a black hole. It does not possess enough mass for gravity to crush its core beyond all known forms of support. Instead, after swelling into a red giant and shedding its outer layers, it will leave behind a white dwarf, a hot, dense, stellar ember, roughly the size of Earth. The white dwarf no longer produces energy through ordinary fusion. It survives because quantum physics prevents its electrons from being squeezed into identical states. This resistance, called electron degeneracy pressure, is not heat, and it does not fade in the same way ordinary gas pressure does. That idea is one of the first hints that dead stars can be deeply unfamiliar. In daily life, pressure usually comes from particles moving and colliding. Heat a gas, and its particles move faster, pushing more strongly against the walls of a container. Cool it, and the pressure decreases. Degeneracy pressure is different. It arises from the rules governing particles such as electrons. Even at very low temperatures, electrons cannot all occupy the same quantum state. When matter is compressed, they are forced into higher and higher momentum states, and this creates a powerful resistance to further squeezing. A white dwarf is therefore supported by a rule of quantum identity, not by fire. There is, however, a limit to how much mass electron degeneracy pressure can support. If the white dwarf becomes too massive, especially by pulling material from a companion star or merging with another white dwarf, gravity gains the advantage. The critical mass is about 4 times the mass of the Sun, though the precise outcome depends on composition, rotation, and other details. Beyond that threshold, known as the Chandrasekhar limit, the electrons can no longer maintain the star's structure. In some cases, the object explodes as a type of supernova. In others, the collapse continues toward an even denser remnant. For stars born with much greater mass than the Sun, the final stages are more dramatic. As their cores evolve, they fuse progressively heavier elements. Hydrogen becomes helium. Helium can become carbon and oxygen. And in the most massive stars, further reactions produce elements such as neon, magnesium, silicon, and eventually iron. Each stage is shorter than the one before. Hydrogen burning may last millions of years, while the final silicon burning stage can last only days. The star is moving toward a boundary because iron cannot release useful energy through fusion in the same way lighter elements can. Once an iron core grows too massive, the old balance fails with extraordinary speed. The collapse of an iron core is not a slow settling. It unfolds in a fraction of a second. Electrons are driven into protons, producing neutrons and neutrinos. The core contracts from something roughly the size of Earth to an object only tens of kilometers across. Matter reaches densities comparable to those inside atomic nuclei, and the inner core stiffens abruptly. The surrounding material continues falling inward, strikes the compressed core, and helps generate a shock wave. Neutrinos, released in almost unimaginable numbers, carry away most of the collapse energy and may help revive the shock. The outer layers of the star can then be blasted into space in a core collapse supernova. What remains at the center depends on how much mass the collapsed core retains. If it is not too massive, gravity is halted once again, but this time not by electrons. The remnant becomes a neutron star, an object that may contain more mass than the Sun inside a sphere about the size of a city. A teaspoon of its matter, if it could somehow be removed and remain intact under earthly conditions, would weigh billions of tons. Yet even that familiar comparison is misleading, because neutron star matter cannot simply be scooped out. Its extraordinary state exists only under crushing pressure, and away from that pressure, it would change violently into more ordinary forms. Density here is not merely an impressive number, it changes what matter is allowed to become. A neutron star is often described as a giant atomic nucleus, but that image is only partly correct. It captures the density, though not the internal complexity. The outermost layer may contain atomic nuclei arranged in a rigid crystal, with electrons moving through them. Deeper down, the nuclei become increasingly rich in neutrons. Eventually, neutrons begin to leak out, forming a strange mixture of nuclear clusters, free neutrons, and electrons. Still deeper, the nuclei may stretch into shapes that physicists informally call nuclear pasta, sheets, tubes, and tangled structures produced by the competition between nuclear attraction and electrical repulsion. These structures may be among the strongest known materials, although their exact arrangement remains a subject of active research. Below these layers lies a region that cannot be reproduced directly in any laboratory. Neutrons may flow as a superfluid, moving without ordinary viscosity, while protons may form a superconducting component that carries electrical currents with almost no resistance. These phases could influence how the star cools, rotates, and responds to stress. They may also help explain glitches, sudden tiny increases in the rotation rate of some pulsars. A glitch might occur when angular momentum stored in the superfluid interior is transferred to the solid crust. Even a small change can reveal that the star is not a simple ball, but a coupled system of layers behaving according to different quantum rules. Some neutron stars announce themselves as pulsars. Their magnetic fields channel radiation into beams that sweep through space as the star rotates. When one of those beams crosses Earth, telescopes detect a pulse, regular enough in some cases to rival the stability of atomic clocks. The pulsar does not switch on and off. It is more like a cosmic lighthouse turning through the darkness. Because the original star contracts so dramatically, its rotation speeds up, just as a spinning skater rotates faster when drawing in their arms. A newborn neutron star may spin many times each second, while recycled pulsars can rotate hundreds of times per second. Their magnetic fields can be equally astonishing. Some neutron stars, called magnetars, possess fields far stronger than those of ordinary pulsars. Near the surface, a magnetar's field can be around a quadrillion times stronger than Earth's magnetic field. At such strengths, atoms may become distorted, and the vacuum itself can display quantum effects that would be imperceptible under ordinary conditions. Magnetars sometimes release sudden bursts of X-rays and gamma rays, possibly when their crusts fracture or magnetic fields rearrange. These events sound violent, and they are, but from across the galaxy they arrive as brief signals, small ripples of information carrying news from matter under extreme stress. It is tempting to think that neutron stars are simply the final stable step before black holes, but the word stable must be used carefully. Physicists still do not know the exact maximum mass a neutron star can support. Observations show that some neutron stars contain about twice the Sun's mass, so any successful theory of dense matter must support at least that much. Above some larger threshold, gravity should overwhelm all known pressure and force the object to collapse into a black hole. The threshold depends on the equation of state, the relationship between pressure, density, temperature, and composition inside matter that no experiment can fully recreate. This uncertainty opens the door to stranger possibilities. At densities several times greater than those inside ordinary atomic nuclei, neutrons may no longer remain distinct particles. They are made of quarks, and under enough pressure, quarks might move more freely through a new phase of matter. Other particles, such as hyperon, might appear. Some models suggest condensates of short-lived particles could form. These are not established descriptions of real stars. They are theoretical possibilities allowed by current physics, constrained by nuclear experiments and astronomical observations but not yet confirmed. The deeper we imagine descending into a neutron star, the less certain the map becomes. A black hole, by contrast, can appear surprisingly simple from the outside. Once matter falls behind the event horizon, distant observers can describe the settled black hole using only a few overall properties, mainly mass, spin, and electric charge. The detailed structure of the original star seems to disappear from view. A neutron star may therefore be more complicated in one sense, even if it is less extreme in another. It has a surface. It can crack, ring, cool, pulse, deform, and collide. Its internal matter can pass through multiple phases. A black hole hides its interior, while a compact star leaves clues at the boundary. So the question is not whether anything can exceed a black hole in gravitational intensity. According to general relativity, a black hole represents collapse beyond the formation of an event horizon, and no ordinary star can be more compact without becoming one. The more subtle question is whether a dead star can be stranger in composition, behavior, or hidden structure. Could it contain quark matter, a nearly perfect superfluid, or a stable substance unlike any material on Earth? Could two objects with almost the same mass and size have entirely different interiors? And could the universe be quietly producing such remnants without our yet knowing how to recognize them? For now, we remain near the surface of the mystery. We have watched stars hold themselves up with heat, then with quantum pressure, and finally with the resistance of nuclear matter. Each time gravity tightens its grip, nature answers with a deeper layer of physics. The death of a star is not merely an ending, it is a gradual stripping away of the familiar, until temperature, density, magnetism, relativity, and quantum mechanics meet within a sphere small enough to fit inside a city. In the next stage of the journey, we will follow the collapse more closely, toward the moment when atoms can no longer remain atoms, when a massive star reaches the final hours of its life, The change begins deep inside a region that no telescope can see directly. For millions of years, the core has been warmed and supported by nuclear reactions, but once iron has accumulated, fusion can no longer provide the energy needed to resist gravity. Iron is unusually stable. Combining iron nuclei does not release energy in the way that fusing lighter elements does, and splitting them also requires energy. The star has reached a kind of nuclear dead end. Above the core, layers of lighter elements may still be burning, but the center has lost the ability to support the weight pressing down upon it. The iron core is already extraordinarily dense before the final collapse begins. Electrons move through the matter at speeds approaching the speed of light, and their quantum pressure helps hold the core up. Yet the core continues to gain mass as nuclear burning in the surrounding layers produces more iron group elements. Eventually, it passes a threshold beyond which electron degeneracy pressure can no longer maintain equilibrium. The transition is not announced by a visible crack or a slow dimming of the star. Deep within the core, gravity simply begins to win. Once contraction starts, it accelerates rapidly, because the very act of compression triggers processes that remove the remaining sources of support. One of those processes is electron capture. Under ordinary conditions, protons and electrons can remain separate within atoms. During core collapse, however, the density becomes so great that energetic electrons are driven into protons. A proton and an electron combine through the weak nuclear interaction, producing a neutron and an electron neutrino. This reaction reduces the number of free electrons, weakening the degeneracy pressure that had been resisting gravity. The core therefore contracts faster, causing still more electron captures. What begins as instability becomes a runaway. Matter is no longer merely being packed more tightly. Its identity is changing as protons and electrons are converted into neutrons. At nearly the same time, intense gamma radiation begins breaking heavy nuclei apart. This process, called photodisintegration, consumes energy rather than releasing it. Iron nuclei are dismantled into smaller particles, including helium nuclei and individual protons and neutrons. The energy that once helped support the core is absorbed into the work of unbinding nuclear matter. Electron capture and photodisintegration therefore cooperate with gravity, each one removing pressure or energy that might have slowed the collapse. The inner core falls inward at a significant fraction of the speed of light, in less than a second. A region once thousands of kilometers across contracts toward the scale of a city. During the early collapse, neutrinos escape relatively easily. These ghost-like particles interact so weakly with matter that vast numbers can pass through ordinary planets without striking anything. But the collapsing core is not ordinary matter. As the density rises, even neutrinos begin to scatter often enough that they become temporarily trapped. They can no longer leave immediately and instead move outward through countless interactions. A new kind of boundary develops, sometimes called the neutrinosphere, beyond which neutrinos can finally stream freely into space. Most of the gravitational energy released in the collapse eventually leaves in the form of neutrinos, not visible light, making the explosion fundamentally different from the bright appearance seen through telescopes. The inner part of the core collapses somewhat differently from the outer part. Sound waves and pressure changes can still travel quickly enough through the innermost region to keep it moving in a roughly coordinated way. Farther out, matter falls inward more independently and at greater speed. When the central density approaches that found inside atomic nuclei, the behavior of the strong nuclear force changes. At moderate distances, this force binds protons and neutrons together. When those particles are pushed too close, however, the interaction becomes strongly resistant to further compression. The inner core suddenly stiffens. Its inward fall slows abruptly, while the outer material continues rushing toward it. This abrupt halt is often described as the core bounce. The innermost material compresses, resists, and expands slightly, launching a shock wave outward. For a time, early models suggested that this shock might directly blow apart the star. The reality appears more complicated. The shock loses energy as it travels through the infalling iron core. It must break apart heavy nuclei, and energy also escapes through neutrinos. Instead of sweeping cleanly through the entire star, the shock often stalls within a few hundred kilometers of the center. The star has not yet exploded. It has entered a brief and delicate phase in which collapse, neutrino transport, turbulence, and nuclear physics all compete. Neutrinos may help revive the stalled shock. Although they interact weakly, their numbers and energies are immense. A small fraction of the neutrinos streaming outward can deposit energy into the matter behind the shock. Convection and turbulent motion may keep this material in the heating region long enough for the shock to regain strength. Large-scale instabilities can cause the stalled shock to wobble and deform, creating more favorable conditions for an explosion. Researchers continue to study the exact combination of processes involved. Using complex computer simulations, core collapse supernovae are understood in broad outline, but predicting every explosion from first principles remains one of the most difficult problems in astrophysics. When the shock finally moves outward successfully, it tears through the star's surrounding layers. Elements forged during the star's life are thrown into space, joined by new elements produced in the explosion and in the extreme environments nearby. The visible supernova can briefly shine as brightly as an entire galaxy, yet the light represents only a small share of the released energy. Deep inside, the newly formed compact object remains buried beneath hot, expanding debris. The remnant is initially called a proto-neutron star. It is larger, hotter, and richer in trapped neutrinos than the cooler neutron star it may eventually become. Over the following seconds, it contracts and loses energy as neutrinos carry heat away. A proto-neutron star begins with temperatures of tens of billions of degrees. At such temperatures, matter is not arranged like the cold layers often shown in simplified diagrams of mature neutron stars. Particles move with enormous energies. Neutrinos remain abundant, and the composition changes as the object cools. Over tens of seconds, the star releases a vast neutrino signal and shrinks toward a radius of roughly 10 to 15 kilometers, depending on its mass and internal physics. The first detected neutrinos from a supernova outside the solar system arrived from supernova 1987A. Only a few dozen were recorded, yet they confirm that stellar collapse releases most of its energy invisibly through neutrinos. The transformation from an ordinary stellar core into neutron-rich matter is sometimes called neutronization. Though the final object is not made exclusively of neutrons, protons, electrons, and perhaps other particles remain present in smaller amounts. The balance among them is controlled by pressure, density, temperature, and weak interactions. If too many protons and electrons are present, electron capture produces more neutrons. If conditions favor the reverse process, neutrons can transform through beta decay. Deep inside the star, matter settles toward a state of chemical equilibrium. Though the exact composition depends on uncertain nuclear behavior at densities beyond those measured directly in laboratories, it is useful to pause and consider how complete the destruction of atoms really is. An atom is mostly empty space, with a tiny nucleus surrounded by an electron cloud. In the collapsing core, that familiar architecture cannot survive. The electrons are no longer attached to individual nuclei in the ordinary sense. The nuclei themselves are forced so close together that their boundaries lose their usual meaning. At greater depths, many neutrons escape from nuclei and flow through the material. Matter becomes a continuous quantum system rather than a collection of recognizable atoms. The periodic table, so useful on Earth, no longer provides a complete language for describing what exists there. The resistance that stops the collapse is often attributed simply to neutron degeneracy pressure. But the full story is more subtle. Neutrons are fermions, so they obey the same exclusion principle that supports electrons in white dwarfs. They cannot all occupy identical quantum states, and compression forces them into increasingly energetic configurations. Yet interactions between neutrons and other particles also contribute greatly to the pressure. The strong nuclear force can be attractive at some distances and repulsive at shorter ones. The structure of a neutron star, therefore, depends not only on a simple quantum rule, but on a complicated many-body problem involving countless strongly interacting particles under extreme gravitational curvature. This is where the equation of state becomes essential. In everyday language, an equation of state tells us how a material responds when it is compressed or heated. For gases, the relationship can sometimes be described by a compact formula. For neutron star matter, the equation of state must account for nuclear forces, quantum mechanics, relativity, and possibly new particles or phases. A relatively stiff equation of state means pressure rises quickly as density increases, allowing a star to support more mass and maintain a larger radius. A softer equation of state permits matter to compress more easily, producing a smaller star and potentially lowering the maximum stable mass. No laboratory can create a piece of cold neutron star matter and hold it for direct examination. Particle accelerators can collide heavy nuclei and briefly produce high-density matter. But these experiments differ in temperature, composition, and duration from the interior of a neutron star. Nuclear theory and laboratory measurements provide important constraints, especially near the density of atomic nuclei. Yet uncertainty grows at higher densities. Astronomers must therefore treat the star itself as the experiment. By measuring mass, radius, cooling behavior, rotation, and deformation, they try to infer how matter behaves where direct access is impossible. Every compact star becomes a distant pressure chamber designed by gravity. Gravity in a neutron star must be described by Einstein's general theory of relativity. Newtonian gravity offers useful intuition, but it is not accurate enough for an object this compact. The star's mass curves space-time strongly, altering both its structure and the path of light leaving its surface. A photon climbing away loses energy and becomes redshifted. Light can also bend around the star, allowing a distant observer to see more than half of the surface at once. Time passes slightly more slowly near the surface than it does far away. These effects are substantial, though an ordinary neutron star still has no event horizon. The distinction between a neutron star and a black hole is governed by compactness, the amount of mass contained within a given radius. As more mass is added to a neutron star, the central pressure must increase to support it. Yet, in relativity, pressure itself contributes to gravity. The very thing resisting collapse also strengthens the gravitational field. This creates an upper limit that cannot be avoided simply by making the internal pressure larger. At some point, no stable arrangement of ordinary neutron star matter is possible. The exact threshold is uncertain, but it is expected to lie somewhere above the heaviest neutron stars observed and below masses where compact objects are confidently identified as black holes. Rotation can temporarily help support a star. A rapidly spinning neutron star experiences an outward rotational effect that reduces the pressure required near its equator. A remnant that would collapse if it were not rotating may remain stable for a time while spinning quickly. As it loses rotational energy through electromagnetic radiation or gravitational waves, it can cross the stability threshold and collapse later. Differential rotation, in which different layers spin at different rates, may provide even stronger temporary support in the aftermath of a merger. Such objects are called supermassive or hypermassive neutron stars, depending on the kind of support involved and the mass they contain. This delayed collapse may occur when two neutron stars merge. As they spiral together, they radiate gravitational waves and eventually collide at a significant fraction of the speed of light. The immediate result can be a black hole, a temporarily supported massive neutron star, or perhaps a longer-lived remnant. Depending on the total mass and the uncertain equation of state, the merger compresses and heats matter in ways different from an isolated stellar collapse. It also ejects neutron-rich material into space, creating conditions where many heavy elements can form. Gold, platinum, and other nuclei may be produced during rapid neutron capture in these violent but scientifically revealing events. Even before such mergers were detected through gravitational waves, theorists understood that the final boundary between neutron stars and black holes contained important clues about matter. A star that supports two solar masses rules out equations of state that are too soft. A precisely measured radius can reveal how compressible the interior is. The gravitational wave signal from a merger records how each star deforms in the tidal field of the other. A compact, easily compressed star responds differently from a larger, stiffer one. The collision, therefore, carries information from matter that is otherwise hidden beneath an opaque surface and an intense gravitational field. Yet collapse itself may conceal the answer. If the remnant becomes a black hole quickly, the complex phases of matter inside it disappear behind an event horizon before they can produce long-lasting signals. If it survives even briefly, its oscillation, magnetic fields, neutrino emission, and gravitational waves may reveal traces of its internal structure. Astrophysicists search for these traces because the transition is not merely between one object and another. It is a transition between two kinds of mystery: a material object with an uncertain interior and a black hole whose interior is inaccessible to distant observers. The story of stellar collapse is therefore a sequence of disappearing supports. Thermal pressure fails when fuel is exhausted. Electron degeneracy fails when the core grows too massive. Atomic nuclei dissolve as density rises. Neutron-rich matter resists for a time through quantum mechanics and the strong nuclear force. Beyond that, perhaps new phases emerge, or perhaps gravity continues without pause toward an event horizon. Nature does not reveal in advance which defense will be the last. It simply increases the pressure until the next layer of physical law must answer. And so, in the remains of a dead star, atoms have not merely been crushed into smaller versions of themselves. Their structure has been erased and reorganized. Electrons and protons have combined. Nuclei have merged into a dense quantum landscape. Neutrinos have carried away the heat of collapse. Gravity has transformed a stellar core larger than a planet into an object no wider than a city. What lies beneath its crust may be mostly neutrons. But that familiar word may hide a far more intricate reality. To understand how strange the remnant can become, we must now descend into the neutron star itself. To enter a neutron star in imagination, we must first leave behind nearly every instinct built from life on Earth. There is no ordinary ground, no atmosphere in the familiar sense, and no gentle transition from surface to interior. Gravity near the crust may be more than 100 billion times stronger than Earth's. A small fall would release enormous energy, and any normal object approaching the surface would be torn apart, heated, and transformed long before arrival. Yet the star itself is not a featureless sphere. It is layered, dynamic, and alive with motion. Beneath a thin outer atmosphere lies a solid crust, and beneath that crust begins a sequence of strange states of matter that become less certain the deeper we go. The outer atmosphere may be only centimeters thick, though its exact structure depends on temperature, magnetic field, and surface composition. Because gravity is so strong, the lightest elements float upward while heavier ones sink, producing a kind of rapid chemical sorting. Hydrogen, helium, carbon, or heavier nuclei may dominate the visible surface. Radiation escaping from this layer carries clues about the star's temperature and radius, but interpreting those clues is difficult. Strong magnetic fields reshape the behavior of atoms and alter how light travels through the atmosphere. Even a thin coating of material can change the spectrum enough to affect what astronomers infer about the hidden object below. Even the idea of a surface becomes unusual here. There is no gentle shoreline between vacuum and matter. Density rises rapidly over a very short distance, and the material beneath the atmosphere may already be so tightly bound that ordinary chemistry has little relevance. If you could somehow stand there without being destroyed, the horizon would appear strangely curved because the star is so small, while the sky overhead would be distorted by gravity. Light from the far side could bend into view, making the compact sphere seem visually larger than its true outline. The surface is therefore both physically severe and optically deceptive, a boundary where relativity and condensed matter meet. Under the atmosphere lies the outer crust, a rigid lattice of atomic nuclei immersed in a sea of electrons. These nuclei are not the familiar stable elements found on Earth. As pressure increases, electrons are forced into higher energies and are captured by protons inside nuclei, converting them into neutrons. The nuclei therefore become increasingly neutron-rich, moving far beyond the combinations that can survive under ordinary conditions. They arrange themselves in a crystalline structure because their positive charges repel one another, while the surrounding electrons provide balance. This crust may be only about a kilometre thick, yet it can support mountains, though those mountains would likely rise only centimetres or metres before gravity flattened them. The word solid may sound reassuring, but neutron star crust is unlike any solid we know. Simulations suggest it could be billions of times stronger than steel because of its immense pressure and the way nuclear forces bind its structure. Still, the crust is not perfectly unbreakable. As the star spins down, cools, or undergoes magnetic stress, its shape and internal forces slowly change. Tension can build until part of the crust shifts or fractures in a starquake. Such an event may alter the rotation of the star, release bursts of radiation, or disturb the magnetic field, magnetars, where the magnetic field is extraordinarily intense. The crust may be strained continuously by forces rising from deeper layers. The crust also stores the history of the star. As the neutron star cools from its birth, the outer layers freeze into a solid lattice, trapping defects, stresses, and perhaps regions with slightly different compositions. Material later pulled from a companion star can be compressed downward, undergoing a sequence of nuclear reactions that replace the original crust with an accreted one. These reactions release heat deep below the surface and can influence the glow observed after an accreting system becomes quiet. By watching that glow fade, astronomers estimate how quickly heat travels through the crust and how strongly the crust is connected to the colder core. Deeper in the crust, pressure becomes great enough that some neutrons can no longer remain bound inside nuclei. They begin to drip out, giving the region its name, the neutron drip layer. Here, a lattice of neutron-rich nuclei coexists with free neutrons and highly energetic electrons. The free neutrons are expected to form a superfluid, a quantum state in which they move with almost no ordinary viscosity. This does not mean the material is motionless. A superfluid can carry rotation in the form of tiny quantized vortices, each one a microscopic whirl whose circulation is fixed by quantum mechanics. Vast numbers of these vortices may thread the star's interior. As density rises further, the nuclei themselves may cease to resemble compact spheres. The attractive, strong nuclear force pulls nearby nucleons together, while electrical repulsion pushes positively charged protons apart. Under extreme compression, this competition may produce elongated rods, flat sheets, tubes, and bubbles. Physicists playfully call these shapes nuclear pasta, using names such as spaghetti and lasagna. Though the actual physics is anything but playful, these structures could influence how heat, electricity, and neutrinos move through the crust. They may also affect how the crust breaks or couples to the fluid below. making them relevant to signals that telescopes can detect from thousands of light years away. At the base of the crust, individual nuclei may finally dissolve into more uniform nuclear matter. The boundary is not necessarily sharp, and the precise transition depends on the uncertain equation of state. Below it lies the outer core, thought to contain mostly neutrons with a smaller fraction of protons, electrons, and perhaps muons. The pressure is immense, yet the matter may remain fluid. Here, neutrons are expected to form a superfluid, while protons may pair into a superconducting state. Both phenomena arise because particles can join into pairs that behave collectively, allowing the material to flow or conduct current in ways impossible for an ordinary liquid or metal. Superfluidity changes how a neutron star stores and transfers rotation. In a normal fluid, rotational motion can be distributed continuously. In a superfluid, rotation is carried by quantized vortices. As the star gradually loses angular momentum through radiation and particle winds, the solid crust slows down. The superfluid may not slow at exactly the same rate, because some vortices become pinned to structures in the crust. Stress then accumulates between the crust and the superfluid. When many vortices suddenly move or unpin, angular momentum can be transferred outward, causing the visible crust to speed up slightly. Astronomers observe this as a pulsar glitch, a tiny but abrupt change in rotational frequency. A glitch may alter the length of a pulsar's day by only a minuscule amount. Yet, it opens a window into matter we cannot touch. The way the star recovers after the glitch can reveal how strongly its internal layers are coupled. Some parts may adjust within seconds, while others relax over days, months, or longer. Different pulsars show different patterns, suggesting variations in temperature, age, magnetic structure, and interior composition. No single model explains every event perfectly. Some glitches may involve crustal superfluidity, while others may require deeper participation from the core. In this way, a distant pulse arriving through a radio telescope becomes an indirect probe of quantum matter. The superconducting protons in the core may also shape the magnetic field. In an ordinary superconductor, magnetic flux can be expelled or confined into narrow tubes. Something similar may occur inside neutron stars, where magnetic flux could be organized into countless quantized structures. These flux tubes may interact with neutron vortices, linking the star's rotation to its magnetic evolution. If vortices move outward as the star slows, they may drag or cut through magnetic structures, dissipating energy and rearranging the field over long periods. The details are uncertain, but this coupling could help explain why neutron star magnetism changes with age and why some objects behave far more violently than others. The relationship between crust and core is especially important because neither behaves in isolation. A magnetic disturbance can begin deep inside, travel upward, and fracture the crust. A rotational imbalance can develop in the superfluid, then appear suddenly as a measurable change in the surface pulse. Heat generated by nuclear reactions can diffuse inward as well as outward. The star is therefore a coupled object, with mechanical, thermal, magnetic, and quantum processes continually influencing one another. A signal detected at the surface may carry the delayed consequence of an event that began kilometers below, hidden in matter through which no camera could ever look. Cooling offers another way to study the interior. A newborn neutron star begins extraordinarily hot, then loses energy mainly through neutrino emission from its core, and later through photons from its surface. Different reactions produce neutrinos at different rates. Some processes are relatively slow, while others can cool the star rapidly if the density and composition allow them. Superfluidity can suppress certain reactions, but the formation and breaking of particle pairs can also produce neutrinos of its own. By estimating the ages and surface temperatures of neutron stars, Astronomers compare observed cooling patterns with theoretical models, searching for signs of what particles and phases may exist inside. The surface does not always cool evenly. Strong magnetic fields guide heat more easily in some directions than others, creating hot regions near magnetic poles and cooler areas elsewhere. As the star rotates, these regions move in and out of view, causing rhythmic changes in X-ray brightness. General relativity bends the outgoing light, allowing observers to see portions of the far side at the same time. By modelling the changing pulse shape, astronomers can estimate the star's mass and radius. These measurements are delicate because they depend on assumptions about atmospheric composition, magnetic geometry, distance, and instrument response. But together they constrain how compressible dense matter can be. A neutron star also rings. A quake, flare, collision, or sudden rearrangement can excite oscillations that travel through the crust and fluid interior. Different modes involve different patterns of motion, much as a musical instrument can vibrate in several harmonics. In principle, the frequencies of these oscillations depend on the star's mass, radius, crust thickness, magnetic field, and internal composition. Detecting and identifying them reliably is extremely difficult. Yet magnetar flares have shown patterns that may be related to seismic vibrations. If neutron star astroseismology becomes precise, it could allow scientists to infer the internal structure of a compact star from the way it trembles. Rotation itself can deform the star. A rapidly spinning neutron star bulges slightly at the equator, while mountains or internal asymmetries can create tiny departures from perfect symmetry. Because the star is so dense, even a deformation smaller than a grain of sand in relative terms can matter. A rotating asymmetry should emit continuous gravitational waves, carrying energy away at twice the rotation frequency in the simplest case. Detectors have not yet found an unambiguous continuous signal from a known neutron star, but improving searches place limits on how distorted these objects can be. The absence of a signal is still information, narrowing the range of possible crustal strengths and internal magnetic structures. The deepest region, the inner core, is where confidence begins to fade. Densities may reach several times that of an atomic nucleus, and theoretical predictions diverge. The matter might remain a mixture dominated by neutrons and protons, or new particles could appear. The interactions among particles become difficult to calculate because the strong force is complex in this regime. Small differences in theoretical assumptions can lead to large differences in predicted pressure, radius, and maximum mass. The inner core may occupy only part of the star's volume, but it contains a substantial fraction of its mass and may determine whether the object survives as a neutron star or eventually collapses. This uncertainty does not make the science empty. It makes every observation more valuable. A measured mass near 2 solar masses tells us the core cannot be too easy to compress. A small radius would suggest softer matter, while a larger radius would favour stronger pressure at a given density. Cooling curves, glitches, oscillation, and gravitational waves each illuminate a different aspect of the same hidden object. None provides a complete picture alone. Together, they form a kind of slow conversation between theory and the sky, with each new signal narrowing the possibilities and revealing where our understanding remains incomplete. From the outside, a neutron star may appear as a faint point, a regular pulse, or a quiet source of X-rays. Inside, it is a layered quantum world, a crystalline crust, neutron-rich nuclei, superfluid currents, superconducting charges, magnetic flux tubes, and perhaps something still more exotic at the center. Its apparent simplicity is an illusion created by distance. The deeper we descend, the less matter resembles anything familiar. and the more the star becomes a natural experiment performed under conditions no laboratory can sustain. Yet even neutrons may not be the final form. Under greater pressure, they themselves may begin to lose their identity, opening the way to matter beyond neutrons. Deep in the inner core of a neutron star, pressure may become so extreme that even the word neutron begins to lose its usefulness. A neutron is not a fundamental particle. It is made of 3 quarks, bound together by the strong interaction, surrounded by a restless quantum environment of gluons and short-lived particle pairs. Under ordinary conditions, quarks remain confined inside protons and neutrons. They cannot be isolated and carried away like electrons. But when matter is compressed to several times the density of an atomic nucleus, the boundaries between neighbouring neutrons may begin to overlap. The particles may still exist, or they may gradually merge into a new collective state in which quarks move through a larger region of matter. This possible transition is difficult to describe because the strong interaction becomes mathematically challenging under the conditions inside a cold, denser star. At very high temperatures, such as those created briefly in particle colliders, quarks and gluons can form a quark-gluon plasma. The early universe almost certainly passed through such a state during its first moments. A neutron star core is different. It is relatively cold in the language of nuclear physics, even if its temperature would seem enormous by human standards, and it contains a great excess of matter over antimatter. Calculations that work well in some other regimes become much harder here, leaving theorists to compare many plausible models rather than rely on a single exact prediction. If neutrons dissolve into quark matter, the most common quarks at first would likely be up and down quarks, the same types found inside protons and neutrons. Electrons might still be needed to balance electric charge. At greater density, strange quarks could become energetically favourable. The word strange is a technical name inherited from particle physics, but it is unusually appropriate. Strange quarks are heavier than up and down quarks, and they do not form the stable matter around us. Yet under sufficient pressure, replacing some energetic up or down quarks with strange quarks might lower the overall energy of the system. The core could then become a mixture of 3 quark flavors arranged in a state unlike any lasting material known on Earth. This possibility leads to the idea of a hybrid star. From the outside, it might resemble an ordinary neutron star, with a solid crust and layers of neutron-rich matter. At the center, however, it could contain a core of deconfined quarks. The transition between the 2 phases might occur gradually, with hadrons and quark matter blending over a range of densities, or sharply, like water suddenly freezing into ice. The answer depends on the still unknown behavior of dense nuclear matter. 2 stars with nearly identical masses might even possess different interiors if one has crossed the threshold for quark formation and the other has not. A sharp transition could produce an especially curious possibility, sometimes called twin stars. These would be compact stars with similar masses but noticeably different radii. One branch would consist mainly of conventional neutron-rich matter, while the other would contain a large core of a denser phase. They would not be twins because they formed together, but because their measured masses could be almost the same while their internal structures differed profoundly. Detecting such a pattern would offer powerful evidence for a phase transition. For now, twin stars remain theoretical. Measurements of neutron star radii are improving, but they are not yet precise enough to establish this phenomenon with confidence. Quark matter itself may not behave like an ordinary fluid of individual particles. At high density and low temperature, quarks are expected to pair, somewhat as electrons pair in a conventional superconductor. These pairs could form phases known as color superconductors. The word color here refers not to visible color, but to the type of charge associated with the strong interaction. Different patterns of pairing are possible, depending on density and the relative numbers and masses of the quark flavors. One especially symmetric possibility is the color flavor locked phase, in which up, down, and strange quarks pair in an intricate collective arrangement. Whether this phase occurs inside real stars is unknown. Such exotic phases would influence the star in subtle ways. They could change how efficiently the core produces neutrinos, how quickly it cools, how it transports heat, and how it responds to rotation. Some color superconducting phases might suppress many low-energy excitations, reducing certain cooling processes. Others could permit new channels of energy loss. Quark matter might also support its own forms of superfluidity and vortices, adding another layer to the already complicated dynamics of the star. Yet none of these effects provides a simple signature. A cooling pattern that seems unusual may also be explained by nuclear superfluidity, magnetic fields, surface composition, or the star's uncertain age. Before quarks become free over large distances, other particles may appear. As density increases, the energy of the neutrons rises. Eventually, it may become favorable for some neutrons to transform into heavier relatives called hyperons. Hyperons contain strange quarks but remain bound particles, similar in broad structure to protons and neutrons. Examples include lambda and sigma particles. On Earth, hyperons are unstable and decay rapidly. Inside a neutron star, continuous interactions and immense pressure could allow them to persist in equilibrium. Their appearance would add new ways for the matter to arrange itself, potentially reducing the pressure at a given density. That reduction creates what physicists call the hyperon puzzle. If hyperons appear easily, many models predict that neutron star matter becomes softer and less able to support heavy stars. Yet astronomers have observed neutron stars with masses around twice that of the Sun. Any realistic model must keep such objects stable. Perhaps the forces among hyperons are more repulsive than early calculations suggested. Perhaps hyperons appear only at higher densities. Perhaps other phases replace them. Or rapid rotation adds temporary support in special cases. The puzzle does not prove that hyperons are absent. It shows that their behavior under extreme pressure is still incompletely understood. Another proposed state involves condensates of mesons, particles that help describe interactions between nucleons under suitable conditions. Negatively charged pions or kaons might accumulate in a shared quantum state. Such a condensate could replace some electrons in maintaining charge balance and alter the star's pressure and cooling behavior. As with hyperons, these possibilities are grounded in known particle physics, but their existence inside neutron stars has not been established. Dense matter offers many competing ways to lower its energy, and the winning arrangement depends on details that are difficult to calculate. Nature may select one phase, several layered phases, or none of the exotic options currently considered. Among the boldest ideas is the strange matter hypothesis. It proposes that matter containing roughly balanced numbers of up, down, and strange quarks might be more stable than ordinary nuclear matter at very high density. If this were true, quark matter would not need to exist only in the central core. An entire compact star could be made largely of strange quark matter, forming what is called a strange star. Such an object might have a very thin crust of ordinary nuclei or, in some models, a quark surface exposed almost directly to space. This remains speculative. The hypothesis has not been confirmed, and ordinary nuclei clearly remain stable under everyday conditions. A strange star could differ from a conventional neutron star in the relationship between its mass and radius. Ordinary neutron stars are held together mainly by gravity, while strange quark matter might be partly self-bound by the strong interaction. Even a low-mass strange star could remain compact, whereas an ordinary neutron star's structure changes differently as its mass decreases. In principle, precise observations might distinguish these patterns. In practice, most known compact stars occupy a range where the predicted properties overlap. atmospheric uncertainties, magnetic fields, rotation, and measurement errors can blur the difference, allowing a strange star to hide behind the appearance of a neutron star. If stable, strange matter existed, a tiny seed of it inside a neutron star might convert surrounding nuclear matter into the strange phase. The conversion could release energy and move through the star as a burning front. Though theoretical descriptions vary widely, this dramatic possibility has inspired many speculative scenarios, but there is no observational proof that such conversions occur. The feared idea that a small piece of strange matter could transform ordinary planets is not supported by current evidence. Strange matter, if it exists at all, may require pressure so intense that it cannot remain stable outside a compact star. Caution is essential whenever theoretical possibilities are carried far beyond the conditions for which they were proposed. There are also ideas more exotic than quark stars. Some models imagine stars containing bosonic particles, which do not obey the same exclusion rule as electrons and neutrons. A boson star could be supported by quantum effects, self-interactions, or both, rather than conventional degeneracy pressure. No known standard model particle is expected to form an astrophysical boson star of the required kind, so such objects would probably involve hypothetical particles, perhaps related to dark matter. They are not standard outcomes of ordinary stellar death. Still, they help physicists explore how compact an object can become without forming a conventional black hole. Boson stars are useful partly because they reveal that compactness alone does not uniquely determine composition. From far away, an exotic object might bend light, orbit with companions, and produce gravitational waves in ways that resemble a black hole or neutron star. The differences might appear only near the surface, during a collision, or in the pattern of oscillations after a merger. A boson star might lack a hard material surface in the ordinary sense, while still having no event horizon. Matter falling toward it could interact with a distributed field rather than strike a crust. These remain hypothetical signatures for hypothetical objects, but they sharpen the question of what astronomical observations truly prove. Another proposed class is the gravistar, short for gravitational vacuum star. In simplified models, a gravistar replaces the black hole interior with a region whose vacuum-like energy produces outward pressure, surrounded by a thin shell of matter. Such an object could be almost as compact as a black hole while avoiding a traditional event horizon or singularity. Gravistars are not established predictions of a complete theory, and no observation requires them. They are best understood as thought experiments testing whether the external appearance of a black hole could arise from a radically different interior. Their value lies as much in clarifying assumptions as in offering a likely description of nature. Some theories also consider objects with surfaces located only a tiny distance outside where a black hole horizon would have formed. These are sometimes grouped under the broad label of exotic compact objects. Depending on the model, they might reflect part of the incoming radiation, trap waves temporarily, or produce delayed echoes after a merger. Searches for gravitational wave echoes have attracted attention, but no convincing and universally accepted detection has emerged. Noise in detectors can imitate weak repeating patterns, and theoretical predictions depend strongly on the object's assumed structure. The absence of clear evidence leaves black holes as the simplest explanation for the darkest compact objects we observe. For objects created directly from dead stars, neutron stars and black holes remain the firmly established outcomes. White dwarfs are observed in great numbers. Neutron stars reveal themselves as pulsars and X-ray sources, and black hole candidates behave in agreement with general relativity. Quark cores, strange stars, hyperon-rich stars, boson stars, and gravistars occupy different levels of speculation. Some extend well-tested nuclear physics into uncertain conditions. Others require new particles or new arrangements of spacetime. Treating them all as equally likely would be misleading. Science advances by keeping possibilities open while weighting them according to evidence. The most realistic exotic interior may not have a clean name. Nature rarely needs to respect the categories drawn in textbooks. A neutron star might contain a crust of nuclei, an outer core of superfluid neutrons and superconducting protons, a mixed region where hadrons and quarks coexist, and a deeper phase with color superconducting matter. Or the transition might be so gradual that no single boundary marks where neutron matter ends and quark matter begins. In quantum physics, a particle can remain meaningful even while its components participate in wider collective behavior. The question of whether quarks are truly free inside the core may therefore have no simple yes or no answer. This uncertainty is reflected in the equation of state. Different exotic particles often soften matter by giving it additional ways to store energy without producing as much pressure. A softer core tends to make the star smaller and lowers the maximum mass it can support, but strong repulsive interactions can stiffen the matter again. A phase transition might soften one density range and stiffen another. Observations of heavy neutron stars require sufficient pressure at high density, but they do not uniquely tell us which particles generate it. Many different microscopic stories can lead to similar macroscopic masses and radii, making the inverse problem exceptionally difficult. One clue may come from the speed of sound inside dense matter. In this context, sound speed describes how quickly a pressure disturbance moves through the material. It depends on how rapidly pressure increases with energy density and cannot exceed the speed of light. Some theoretical models require the sound speed to rise significantly in order to support massive neutron stars while maintaining relatively small radii. This may signal strong interactions or changes in internal degrees of freedom. Yet the interpretation is not unique. The star does not allow us to place a microphone in its core. We infer the behavior indirectly from its global structure. The boundary between ordinary nuclear matter and exotic matter could also reveal itself during a merger. As two neutron stars spiral together, tidal forces compress and deform them. After contact, the remnant oscillates violently at frequencies of thousands of cycles per second. A sudden phase transition in the core could alter those oscillations, accelerate collapse, or change the gravitational wave spectrum. Present detectors are far more sensitive to the in-spiral than to the high-frequency aftermath, so these details remain difficult to measure. Future observatories may listen more clearly to the moment when dense matter is pushed beyond the conditions found in isolated stars. Even without a merger, a spinning star might cross a phase boundary as it ages. Rapid rotation reduces the central density slightly. As the star loses angular momentum and spins more slowly, its center becomes more compressed. If a new phase appears above a threshold density, the core could transform gradually during spin-down. This might subtly affect the star's moment of inertia and alter how its rotation changes over time. Detecting such a signature would require extremely precise timing and a reliable understanding of magnetic braking, glitches, and internal coupling. The possibility is scientifically attractive, but nature rarely provides a clean signal free from competing explanations. The deeper lesson is that matter does not have one permanent identity. Hydrogen inside a living star becomes helium. Iron in a collapsing core is broken apart. Protons and electrons combine into neutrons. Neutrons may overlap, transform into hyperon, or dissolve into quarks. Quarks themselves may pair into collective states. At every stage, the particles are governed by the same underlying laws. Yet pressure and density reveal different arrangements permitted by those laws. A dead star is strange not because physics fails there, but because physics is allowed to express possibilities that ordinary environments keep hidden. Could one of these objects be stranger than a black hole? In terms of internal material complexity, perhaps a hypothetical hybrid or strange star could contain multiple quantum phases, each with distinct particles, vortices, currents, and transition. A black hole, viewed from outside after it settles, appears almost austere. Its observable gravitational field is described mainly by mass and spin, with electric charge expected to be negligible in astrophysical settings. Yet this simplicity may conceal the deepest mystery of all: what happens to information and matter beyond the horizon. Strangeness depends on whether we mean complicated matter, extreme gravity, or the limits of what can ever be observed. For now, exotic dead stars remain possibilities drawn on a map whose outer regions are measured and whose center is still blank. Each new neutron star mass, radius estimate, cooling curve, pulsar glitch, and gravitational wave signal shades in part of that hidden territory. Some theories will eventually be ruled out. Others may converge toward a description no one model currently captures. The core of a dead star may contain quarks, hyperons, condensates, or only intensely interacting neutrons and protons. Whatever the answer, the star is already stranger than its quiet light suggests. We are now ready to compare that hidden complexity with the apparent darkness of a black hole. A black hole seems, at first, to be the natural winner in any contest of cosmic strangeness. It has no visible surface, no material crust, and no place from which light can return once it crosses the event horizon. Around it, space and time are bent so strongly that ordinary intuition becomes unreliable. Yet the word strange can mean more than extreme. It can mean complicated, unpredictable, or filled with hidden structure. By that measure, a dead star that remains just outside the black hole boundary may be stranger in a very different way. It can possess matter, layers, fields, vibrations, and transitions, all exposed indirectly to observation. A mature black hole, viewed from far away, is remarkably simple. According to general relativity, an isolated black hole can be described by only a few measurable properties: its mass, its rotation, and, in principle, its electric charge. Astrophysical black holes are expected to carry almost no lasting net charge, because surrounding matter would quickly neutralize it. This leaves mass and spin as the main features. The original star may have contained countless layers, magnetic fields, chemical elements, and turbulent flows. But after collapse, those details no longer remain visible outside the horizon. The external gravitational field settles into a smooth and elegant form, almost as if the universe has erased the object's biography. This apparent simplicity is captured by the phrase no-hair theorem, a name suggesting that black holes have no elaborate external features, or hair, preserving the detailed nature of what formed them. The theorem applies under specific assumptions, and real black holes in messy astrophysical environments can be surrounded by disks, magnetic fields, and orbiting matter. Still, the black hole itself is expected to be simple. A neutron star is the opposite. Its mass and rotation do not tell the whole story. Its radius, crust thickness, magnetic geometry, temperature, composition, superfluid behavior, and internal phase transitions can all influence what we observe. The star carries traces of its history in ways a settled black hole may not. The event horizon is not a solid membrane. It is a boundary in space-time, defined by the fact that beyond it, all future directed paths lead inward. A person falling across a sufficiently large black hole's horizon would not necessarily feel a sudden impact at that exact location. There would be no wall to strike for a distant observer. However, signals from the falling object would become increasingly delayed, redshifted, and faint. The object would never appear to cross in a simple, direct way. This difference between local experience and distant observation is one reason black holes feel so mysterious. The horizon is real, but it is not a material surface that can crack, glow, or ring like the crust of a star. A neutron star, by contrast, has a true surface, although it is unlike any surface on Earth. Matter falling onto it must eventually collide with the outer layers, releasing energy in X-rays or gamma rays. Gas pulled from a companion star can build up, heat, undergo nuclear reactions, and sometimes explode in thermonuclear bursts. These flashes provide direct evidence that the central object has a surface. If the object were a black hole, the gas could continue inward through the horizon without striking a solid boundary. In this simple observational distinction, the presence or absence of a surface becomes one of the most important clues separating a material star from a region of trapped spacetime. Yet the closer a star becomes to the size at which a horizon would form, the more difficult it is to observe its surface directly. Light struggles to escape, time dilation becomes stronger, and radiation loses more energy as it climbs outward. A hypothetical object with a surface only slightly outside the black hole radius might look dark for long periods. Matter could fall onto it and release energy, but the signal might be delayed, redshifted, or trapped by the intense curvature of space-time. Such an object could imitate a black hole surprisingly well. The question then becomes not merely whether a surface exists, but whether the universe allows us enough time and sensitivity to detect its consequences. General relativity predicts a special circular region around a compact object called the photon sphere, where light can orbit temporarily, around a non-rotating black hole. This lies outside the event horizon. Any object compact enough to fit inside its own photon sphere could trap radiation and gravitational waves for a time, even if it had no horizon. Light might circle repeatedly before escaping, while disturbances could bounce between the surface and the surrounding curvature. This creates the theoretical possibility of delayed signals or echoes. But the existence of a photon sphere does not prove that an object is a black hole, and the detection of weak echoes would require extraordinary care to distinguish real physics from noise. The most famous visual signature of a black hole is its shadow, the dark region produced when light rays are captured or strongly deflected. Images of the supermassive objects at the centers of the galaxy, M87 and the Milky Way, show bright rings surrounding central darkness, consistent with black hole predictions. Yet these images do not photograph the event horizon itself. They reveal radiation from hot plasma moving through curved space-time near the compact object. A sufficiently dark and compact alternative might create a broadly similar pattern. The reason black holes remain the preferred explanation is not that every alternative is logically impossible, but that general relativity describes the observations with remarkable economy and without requiring additional unseen structures. This is an important principle in science. A strange possibility is not automatically a likely one. Theories gain strength when they explain many observations with few assumptions and when their predictions survive repeated tests. Black holes fit the motion of stars, the behavior of accretion disks, the timing of X-ray sources, gravitational wave signals from mergers, and horizon-scale image. Exotic, compact objects must match all of these while also explaining why their distinctive features have remained hidden. Some may still be possible, but the available evidence places increasingly narrow limits on them. Scientific imagination remains open, yet it moves within boundaries drawn by measurement. When two black holes merge, they produce a gravitational wave signal with a distinctive sequence. First comes the inspiral, as the objects circle faster and closer. Then the merger occurs, followed by ringdown. When the newly formed black hole settles into a stable state, the ringdown resembles the fading vibration of a struck bell, except the bell is space-time itself. The frequencies and decay times depend mainly on the final black hole's mass and spin. So far, observed signals are broadly consistent with this picture. If the remnant had a material surface or unusual internal structure, additional oscillations or delayed features might appear, though detecting them reliably remains difficult. A neutron-star merger is far more complicated. The stars deform before contact. Their crusts and cores collide. Matter is heated to extraordinary temperatures, and magnetic fields can be amplified violently. The remnant may oscillate, eject neutron-rich material, form a massive temporary star, or collapse promptly into a black hole. It may produce neutrinos, gamma rays, heavy elements, and a glowing kilonova. The outcome depends sensitively on the equation of state and total mass. Compared with the clean gravitational ring-down of a black hole, the collision of material compact stars is a storm of nuclear, quantum, electromagnetic, and relativistic processes unfolding almost at once. This contrast reveals one answer to the central question. A black hole may be more extreme in compactness, but a neutron star can be more information-rich. Its surface and interior participate in many kinds of physics, each leaving possible traces. A black hole, once settled, hides almost everything behind a horizon. The neutron star remains exposed enough to tell us about its temperature, magnetic field, rotation, crust, and perhaps its core. Its complexity is not a sign that gravity is weaker in an unimportant sense. It is a sign that matter has not yet disappeared from communication. The star still has ways to speak to the universe. The black hole's hidden interior creates a different kind of strangeness. Classical general relativity predicts that collapse continues toward a singularity, a region where curvature becomes infinite, and the theory can no longer provide a complete physical description. Most physicists interpret this not as proof that nature truly contains a literal point of infinite density, but as evidence that general relativity is incomplete in that regime. A quantum theory of gravity would be needed to describe what really happens. The horizon prevents distant observers from testing the interior directly, leaving the deepest part of the black hole beyond ordinary experiment. Its strangeness comes partly from inaccessibility. This inaccessibility leads to the black hole information problem. Quantum mechanics suggests that information about a physical state cannot simply vanish. While the classical description of a black hole seems to erase the detailed identity of matter that falls in, black holes also emit Hawking radiation through quantum effects near the horizon, causing them to lose mass extremely slowly. If the radiation is perfectly thermal and contains no information about what entered, then complete evaporation appears to destroy information. Many proposed solutions exist, but no consensus has fully resolved the problem. Here the black hole becomes stranger not because of exotic matter, but because two successful theories seem to make incompatible demands. A hypothetical exotic star without a horizon might avoid some aspects of the information problem because matter and radiation could, at least in principle, return from its surface. But avoiding a horizon introduces other difficulties. The object must resist enormous gravity without collapsing, remain stable, and reproduce the many observations already explained by black holes. Its surface might become extremely hot as matter accumulates, producing radiation that should be detectable. Its collisions might generate echoes or electromagnetic flashes that have not been clearly observed. Every attempt to replace the horizon with a material boundary solves one mystery only by creating a demanding new set of physical requirements. The difference between a black hole and an exotic star may be very small in radius but enormous in meaning. Imagine compressing several solar masses into a sphere. If the surface remains even slightly outside the critical boundary, signals can still escape. However, slowly. Matter retains some contact with the wider universe. If the boundary passes inside the horizon, every future path from the interior points inward, to a distant observer. The object has crossed from material complexity into causal silence. The transition is not merely a change in density. It is a change in which events can influence the outside world, a rearrangement of the structure of cause and effect. Rotation makes this boundary even more subtle. Real black holes and neutron stars spin, sometimes rapidly. A rotating black hole drags space-time around with it. creating a region outside the horizon called the ergosphere, where nothing can remain perfectly stationary relative to distant space. Energy can, in principle, be extracted from this rotation through interactions with matter or fields. A rapidly spinning neutron star also drags spacetime, but it adds a surface, a magnetic field, and material currents. Two objects with similar masses and spins may therefore shape their surroundings in related ways. While differing completely in what happens at the center, their external resemblance can conceal an internal divide. Some neutron stars may approach the maximum compactness allowed for stable matter, but they cannot become arbitrarily small while remaining ordinary stars. If pressure is increased too much, its contribution to gravity becomes significant. Beyond a critical point, stronger pressure cannot rescue the star because it deepens the curvature it is trying to resist. This relativistic limit means that a stable material object must keep its surface far enough outside its own gravitational radius. Exotic equations of state can shift the boundary, but not remove the logic of collapse. Any proposal for an ultra-compact star must therefore explain how it remains stable without violating causality or well-tested gravitational principles. The strangest possibilities often live close to these limits. A quark star might be denser and smaller than a conventional neutron star while still possessing a surface. A boson star might distribute matter through a quantum field without a normal crust. A gravastar might replace the interior with vacuum-like energy and a thin shell. Each idea changes what lies where a black hole interior would otherwise begin. Yet from the viewpoint of evidence, they remain possibilities rather than established objects. The night sky has given us strong reasons to believe in neutron stars and black holes. It has not yet required us to add these more unusual categories. Perhaps, then, strangeness should not be treated as a ranking. A neutron star is strange because matter survives in forms that challenge intuition. A black hole is strange because matter's detailed structure becomes hidden behind a causal boundary. One object is a laboratory of extreme substance. The other is a laboratory of extreme spacetime. One invites us to ask what matter can become. The other forces us to ask what can be known. Their mysteries overlap near the threshold of collapse, where nuclear physics, quantum theory, and general relativity all become necessary. Yet no single framework provides the entire story. Standing far away in imagination, we can picture the two remnants against the darkness. One may pulse with radio light, crack beneath magnetic stress, cool through neutrinos, and conceal quarks beneath a solid crust. The other may appear almost perfectly dark, revealing itself only through the motion of nearby matter and the curvature it leaves behind. The first is crowded with structure. The second is defined by what it refuses to reveal. Whether one is stranger than the other depends on which mystery feels deeper, the astonishing complexity of matter under pressure, or the silent simplicity of a horizon that separates the observable universe from whatever lies beyond. The universe does not allow us to open a neutron star and examine its layers directly. No probe could survive the approach. No sample could remain stable after removal. And no telescope can see through the dense matter to the core. Yet nature provides other methods. A compact star affects light, time, motion, heat, and space-time itself. Each effect carries information about what the object must be. Astronomers therefore study dead stars by combining many imperfect clues: their masses, radii, temperatures, pulse shapes, rotational changes, collision, and gravitational waves. No single measurement reveals the whole interior, but together they can narrow the possibilities. Much as distant echoes can reveal the shape of a hidden room, mass is one of the most reliable starting points. In a binary system, a neutron star and its companion orbit a shared center of mass. By timing the pulses from a pulsar with extraordinary precision, Astronomers can measure subtle changes caused by orbital motion and relativity. In favorable systems, these effects reveal the neutron star's mass with remarkable accuracy. The existence of neutron stars near twice the mass of the Sun has already ruled out many theories in which dense matter becomes too soft at high pressure. Any proposed equation of state, whether it contains only nucleons or includes quarks and hyperons, must support these heavy stars without allowing them to collapse. Radius is far harder to measure. A neutron star may be only about 20 to 30 kilometers across, yet it is usually hundreds or thousands of light years away. It appears as a point even to powerful telescopes. Astronomers infer its size from the X-rays, leaving the surface, but the signal is altered by gravity, atmospheric composition, magnetic fields, distance, and temperature patterns. Light bends around the star, allowing more than half of the surface to remain visible at once. The amount of bending depends on compactness, the ratio of mass to radius. By modeling how hot regions rotate in and out of view, researchers can estimate which combinations of mass and radius reproduce the observed pulse. These pulse profile measurements require patience and careful uncertainty. A hotspot may not be perfectly circular. The magnetic poles may not lie opposite one another. The atmosphere can beam radiation more strongly in some directions. While rapid rotation changes the star's shape and the energy of arriving photons, different assumptions can shift the inferred radius. Yet as observations improve, the allowed range becomes narrower. If neutron stars of known mass prove relatively large, dense matter must resist compression strongly. If they are smaller, the material may be softer or may undergo a phase transition. A sudden change in radius across stars of similar mass could even hint at two distinct internal families. Another clue comes from thermonuclear X-ray bursts. In some binary systems, a neutron star pulls gas from a companion. Hydrogen and helium accumulate on the surface, compressed beneath newly arriving matter. Eventually, unstable nuclear burning ignites and spreads across the star, producing a bright flash that can last from seconds to minutes. During especially powerful bursts, radiation may briefly lift the outer atmosphere. By studying the brightness, temperature, and apparent emitting area, astronomers attempt to constrain the star's mass and radius. The method is valuable but delicate, because distance, fuel composition, atmospheric behavior, and the geometry of the accretion disk all introduce uncertainty. Cooling neutron stars offer a quieter experiment. After birth, the interior loses energy rapidly through neutrinos, while the surface gradually fades in X-rays. Different particles and phases allow different neutrino-producing reactions. Some processes cool the core slowly, while others can drain energy far more efficiently. Superfluidity may suppress certain reactions once particle pairs form. Yet the formation and breaking of those pairs can also release neutrinos. A star that appears unusually cold for its age may contain rapid cooling channels, though age estimates and surface composition complicate the conclusion. A warm old star may indicate suppressed reactions, internal heating, or a thick, insulating envelope of light elements. Accreting neutron stars provide another version of the cooling test. During periods of active feeding, material falling from a companion compresses the crust and triggers nuclear reactions at increasing depth. These reactions deposit heat below the surface. When accretion stops, the crust cools back toward equilibrium with the core. Astronomers watch the X-ray brightness decline over months or years, measuring how efficiently heat flows through the crust. The cooling curve can reveal the crust's conductivity, impurity level, thickness, and possible superfluid behavior. If the star has undergone several outbursts, repeated observations show whether the interior remembers earlier heating or returns to nearly the same thermal state. Rotation provides some of the most precise clocks in astronomy. A pulsar's repeated beam can be timed over decades, exposing changes far smaller than a human heartbeat. Most pulsars gradually slow as they lose rotational energy. The rate of slowing reflects magnetic torque, particle winds, and perhaps gravitational wave emission. Sudden glitches reveal that the visible crust is exchanging angular momentum with an internal superfluid. The size and recovery of each glitch constrain how much of the star's moment of inertia participates. If the crustal superfluid alone cannot store enough angular momentum, then deeper regions of the core may be involved, revealing how strongly the interior is coupled. The fastest known pulsars also test the strength of compact stars. Rotation pushes matter outward, especially near the equator. If a star spins too quickly, material would no longer remain gravitationally bound and could be shed into space. The limiting frequency depends on mass, radius, and the equation of state. A larger, more easily deformed star reaches this breakup limit at a lower frequency than a smaller, more compact one. The observed population has not yet revealed a neutron star spinning at the absolute theoretical maximum, but every rapidly rotating pulsar excludes some combinations of structure. The apparent absence of extremely fast objects may also reflect how stars are formed. Accrete matter, or lose angular momentum. Magnetars reveal another side of the interior through sudden high-energy activity. Their powerful magnetic fields can twist the crust and magnetosphere, leading to short bursts, prolonged outbursts, and rare giant flares. Some flares show oscillating patterns in their fading X-ray light. These may arise from vibrations of the crust, the magnetic field, or the entire star. If scientists can identify the modes correctly, the frequencies could reveal crust thickness, elasticity, field strength, and coupling to the core. The difficulty is that strong magnetic fields mix different oscillations together, producing a complicated spectrum. The star behaves less like a simple bell and more like an instrument whose strings, body, and surrounding air all vibrate at once. Binary systems can also measure a neutron star's moment of inertia, which describes how its mass is distributed relative to the rotation axis. Two stars with the same mass can have different moments of inertia if one is larger or more centrally condensed. In some relativistic pulsar binarias, long-term timing may eventually reveal this quantity through small changes in the orbit and spin orientation. A precise moment of inertia measurement would provide a powerful test of the equation of state because it combines information about both mass and internal structure. It would not show the core directly, but it would tell us how tightly the star's matter is concentrated. The most dramatic clues arrive when neutron stars collide. Before contact, each star raises a gravitational tide on the other. A stiff star with a larger radius deforms more easily at a given orbital separation, while a compact star resists until the objects are closer together. This deformation alters the gravitational wave signal during the final orbits. The effect is small, but detectors can compare the observed waveform with models and infer a quantity called tidal deformability. The first gravitational wave detection of a neutron star merger showed that the stars were not excessively large and stiff. Later observations continue to refine the range of allowed interiors, though uncertainties remain broad. The merger's electromagnetic light adds independent information. Neutron-rich matter thrown outward undergoes radioactive decay and powers a kilonova, a fading glow that can shift from blue to red as the ejecta expand and form heavy elements. The amount, speed, and composition of the ejected material depend partly on the star's radii, mass ratio, and the lifetime of the remnant. A prompt collapse into a black hole may eject less material through some channels, while a temporarily surviving massive neutron star can supply additional energy and neutrinos. Interpreting the light is complex because nuclear reaction rates and the geometry of the debris remain uncertain, but the event links dense matter physics to the origin of heavy elements. The moments after contact may contain the clearest signature of exotic matter, yet they are also the hardest to hear. The merged remnant can oscillate thousands of times each second, producing high-frequency gravitational waves. The dominant frequencies depend strongly on the remnant's size and stiffness. A transition to quark matter could shift these frequencies, create additional peaks, or accelerate collapse. Present detectors are much less sensitive at such high frequencies than they are during the earlier in-spiral. In most observed events, the post-merger signal has remained beyond clear detection. Future instruments may capture it, turning the brief life of a hypermassive neutron star into a direct laboratory for phase transitions. Neutrinos from a nearby merger or supernova would offer another messenger. They interact weakly enough to escape dense regions that light cannot penetrate, carrying information about temperature, composition, and the formation of a compact remnant. A galactic supernova could send thousands or even millions of neutrinos through modern detectors, depending on its distance and the instruments operating at the time. The time pattern and energy distribution might reveal the birth and cooling of a protoneutron star. If the neutrino signal ended abruptly, it could indicate collapse into a black hole. More subtle features might eventually constrain exotic phases, though extracting them would require detailed and reliable models. Astronomers also search for continuous gravitational waves from rotating neutron stars. A perfectly symmetric star rotating around its symmetry axis would emit none, but a tiny mountain, an internal magnetic distortion, or a misaligned deformation could create a persistent ripple in spacetime. The signal would be extremely weak but nearly steady, allowing detectors to accumulate evidence over long periods. A discovery would measure the degree of asymmetry and test how much strain the crust can support. Different internal phases might sustain different deformations, even without detection. Upper limits tell us that many known pulsars are extraordinarily smooth, with irregularities far smaller than the roughness of ordinary manufactured spheres. Black hole candidates are tested through the absence of surface signals. Matter, falling toward a compact object with a material boundary, should eventually release heat when it strikes. If the object has an event horizon, that energy can disappear from external view. Comparisons between systems thought to contain neutron stars and those thought to contain black holes show differences consistent with this expectation. Researchers also examine gravitational wave ringdowns, orbital motion near galactic centers, and horizon-scale images for deviations from general relativity. So far, the simplest black hole models remain successful. No confirmed echo, surface flash, or anomalous multipole structure has required an exotic replacement. Still, observations rarely deliver a single unmistakable verdict. A small neutron star radius might suggest a phase transition, but it could also arise from ordinary nuclear interactions. Rapid cooling might indicate quark matter, hyperons, or simply an efficient nucleonic process. A delayed collapse after a merger could constrain the maximum mass. Yet the result also depends on rotation and thermal support. The problem is one of degeneracy. Several different interiors can produce similar outward behavior. Scientists overcome this not by trusting one dramatic clue, but by combining many measurements whose uncertainties point in different directions. A successful model must explain heavy masses, radii, cooling, tidis, glitches, and merger outcomes at the same time. This approach is sometimes called multi-messenger astronomy. Light, radio pulses, X-rays, gamma rays, neutrinos, and gravitational waves each respond to different aspects of the same event. Gravitational waves reveal bulk motion and space-time curvature. Electromagnetic radiation reveals hot matter, magnetic fields, and radioactive debris. Neutrinos escape from dense, energetic regions. Precise timing measures rotation and orbital relativity. When all these signals are studied together, the hidden star becomes less hidden. The picture may never be perfectly sharp, but each messenger removes another layer of ambiguity. allowing the internal physics to emerge gradually from a network of independent evidence. Future observatories will expand this conversation. More sensitive gravitational wave detectors may hear the high-frequency ringing after neutron star mergers and detect many more events at greater distances. X-ray telescopes may measure pulse shapes and surface temperatures with improved precision. Radio arrays will discover new pulsars, including rare systems suited for measuring masses, moments of inertia, and relativistic effects. Neutrino observatories will wait quietly for the next nearby supernova. Laboratory experiments and nuclear theory will continue narrowing the behavior of matter near nuclear density. Progress will come not from one instrument alone, but from the slow convergence of astronomy, particle physics, and relativity. Perhaps one day the measurements will reveal a clear discontinuity. Two stars with the same mass but different radii. A merger frequency that ordinary nuclear matter cannot explain. Or a cooling pattern consistent across many objects only when a new phase is included. Perhaps the answer will be less dramatic, showing that neutrons and protons remain meaningful deeper than expected, though interacting in ways more complex than present models capture. Either result would be profound. The goal is not to prove that exotic matter must exist, but to discover which possibilities nature has actually chosen in the hearts of dead stars. For now, the universe offers clues rather than samples. A pulse arrives at a radio dish after travelling through the night. An X-ray photon carries the red-shifted warmth of a distant surface. A gravitational wave stretches Earth by less than the width of a proton, preserving the final motion of two merging stars. Each signal is faint, and each interpretation requires caution. Yet together they allow human beings, resting on one small planet, to investigate matter compressed beyond anything we can create. The final answer remains hidden, but it is no longer silent. The stars are speaking through light, time, and space-time, and we are slowly learning how to listen. At the edge of our understanding, the question is no longer simply whether a dead star can become stranger than a black hole. It becomes a question about what we mean by strange, and about how far human thought can travel when direct experience has ended. A neutron star compresses more mass than the Sun into a sphere no wider than a city. A black hole carries compactness further, beyond the formation of an event horizon. Between them lies a narrow region where matter, gravity, quantum physics, and relativity meet under conditions that no laboratory can reproduce and no human observer can visit. In ordinary life, matter seems dependable. Wood remains wood, iron remains iron, and the ground beneath us appears solid. Yet these familiar forms exist only within a small range of pressure and temperature. Change the conditions enough, and matter reveals hidden possibilities. Atoms lose their electrons. Nuclei break apart. Protons and electrons combine into neutrons. Neutrons may overlap, pair into superfluids, transform into heavier particles, or dissolve into quarks. The objects we call dead stars remind us that the substance of the universe is not fixed in one form. It is a collection of possible arrangements, waiting for nature to provide the right conditions. The death of a star is therefore not an erasure, but a transformation. During its life, a star turns light elements into heavier ones and releases energy into space. When its fuel is exhausted, gravity continues the work. It strips away the structures that once seemed permanent and presses matter toward deeper levels of organization. A white dwarf is supported by electrons. A neutron star is supported by quantum rules and nuclear interactions. A black hole marks the point where no material structure known to us can remain visible outside the horizon. Each remnant is a different answer to the same patient force of gravity. Black holes often appear to represent the ultimate mystery because they hide their interiors. From the outside, a settled black hole can be described with extraordinary simplicity. A neutron star, by contrast, may be a crowded world of layers, currents, vortices, magnetic fields, and phase transitions. One is strange through silence, the other is strange through complexity. The comparison reveals that nature does not offer only one kind of mystery. Some mysteries arise because too much is happening to understand easily. Others arise because the essential events are permanently cut off from observation. Both forms test the boundaries of science in different ways. Science advances by turning these boundaries into questions that can be measured. A pulse arriving a fraction of a second early, an X-ray spectrum altered by gravity, or a faint ripple in space-time can become evidence about matter buried thousands of light-years away. This is one of the quiet achievements of astronomy. Human beings cannot reach a neutron star core, yet we can infer how it responds to pressure. We cannot stand beside a black hole horizon, yet we can test the shape of space-time around it. Distance does not end investigation. It changes the tools, replacing touch with timing, samples with signals, and direct sight with carefully tested inference. There is humility in this method. Every measurement arrives with uncertainty, and every interpretation depends on assumptions that must be examined. A small radius may suggest exotic matter, but it may also reflect ordinary nuclear forces arranged differently than expected. Rapid cooling may reveal a new particle, or it may result from an efficient process already contained within known physics. A gravitational wave feature may carry the signature of a phase transition, or it may be noise. The goal is not to make the universe more dramatic than it is. The goal is to allow the evidence to decide which ideas deserve to survive. That patience protects the wonder rather than diminishing it. A hypothesis does not become less beautiful because it remains unconfirmed. Quark stars, strange matter, hyperon-rich core, and color superconducting phases are valuable partly because they show what known physical laws may permit. Some will prove wrong. Others may turn out to describe only a narrow range of conditions. Perhaps one will become an established part of astronomy. Science does not promise that every imaginative possibility exists. It offers a disciplined way to discover which possibilities nature has chosen, and to let discarded ideas sharpen the questions that remain for future generations. The next generation of observatories may bring the hidden core into clearer focus. More sensitive gravitational wave detectors could hear the brief ringing after neutron stars merge. X-ray telescopes may measure stellar radii with enough precision to reveal sudden changes in internal structure. Radio timing may uncover heavier neutron stars or rare binary systems that expose the distribution of mass inside them. Neutrino detectors may one day record the birth of a neutron star within our own galaxy. None of these signals will carry a label saying quark matter or hyperons. The answer will emerge slowly, through consistency across many kinds of observation. As the data improve, the challenge will not be merely to collect more signals, but to connect them. A radius measured from X-rays must agree with the tidal deformation inferred from gravitational waves. A cooling model must remain compatible with the masses of the heaviest pulsars. A proposed phase transition must survive laboratory constraints from nuclear physics and still produce stars that are stable for millions of years. The strongest explanation will be the one that fits many independent observations without being adjusted separately for each case. In that convergence, an invisible interior may gradually become as scientifically real as any landscape mapped by direct sight. Perhaps the surprising discovery will be that exotic phases are common. The centers of many neutron stars may contain quarks arranged in states that cannot survive anywhere else. Or perhaps nature will prove more conservative, allowing neutrons and protons to remain distinct even at astonishing density. Either outcome would deepen our understanding. Finding exotic matter would reveal a hidden branch of the material world. Failing to find it would show that nuclear matter is more resilient than many models predict. In science, the absence of a hoped-for surprise can itself become a profound result when it closes a door and clarifies the architecture of reality. The question also reaches beyond dead stars. Dense matter connects the oldest moments of the universe with the objects that exist today. Quark matter may resemble, in some respects, conditions that appeared shortly after the Big Bang, though the temperature and particle balance would be very different. Heavy elements created in stellar explosions and neutron star mergers later became part of planets, oceans, machines, and living bodies. The study of compact remnants, therefore, links cosmic beginnings, stellar endings, and ordinary matter around us. The iron in blood and the calcium in bone belong to the same physical story as the crushed cores of distant suns. There is something almost paradoxical in the way destruction creates knowledge. A star must exhaust its fuel, collapse, and sometimes explode before the deepest properties of matter become visible. Two neutron stars must spiral together and collide before their internal stiffness can be written into gravitational waves. A magnetar's crust may have to fracture before its vibrations reveal the strength of its hidden layers. Nature's most violent transitions can become our most delicate instruments. Across enormous distances, the universe transforms catastrophe into information, and that information arrives quietly as a pulse, a spectrum, or a barely measurable change in length. The remnants themselves also participate in a larger cycle. Material thrown from supernovae and neutron star mergers drifts through galaxies, mixing with clouds that may later form new stars and planets. The compact object remains behind, but some of the star's substance begins another history elsewhere. In this sense, stellar death creates both concentration and dispersal. One part is crushed into an object of extraordinary density, while another part is released into the wider universe. The same event can produce a neutron star at the center and the raw ingredients of future worlds beyond it, linking collapse with renewal on scales far longer than a human life. From a human point of view, these scales can feel overwhelming. A neutron star may have existed for millions of years before its light reaches us. Its gravity is strong enough to distort time, while its matter may be compressed beyond any earthly analogy. Yet, understanding begins with small acts, counting pulses, comparing equations, cooling a detector, or watching a faint source over many nights. The grandeur of the subject does not require grand gestures from the people who study it. It is approached through patience, cooperation, and repeated attention to details so slight that they would disappear in ordinary noise. The instruments that make this possible are extensions of human senses, but also of human memory. A telescope records photons too faint for the eye. A radio array compares signals across great distances. A gravitational wave detector notices motions far smaller than an atomic nucleus. Computers preserve years of observations and search for patterns no person could hold at once. Yet every instrument still depends on questions chosen by people and on judgments about uncertainty, error, and meaning. Our knowledge of dead stars is therefore built from both technology and restraint, the ability to detect the nearly undetectable, and the discipline not to claim more than the evidence allows. This may be one reason the night sky can feel both vast and intimate. The objects are unimaginably distant, but the laws that govern them are present here as well. The electrons supporting a white dwarf obey the same quantum rule as electrons in the devices around us. The gravity bending light near a neutron star is the same gravity that holds us to Earth, extended into a more extreme regime. The quarks that may move through a compact star core are the same kinds of quarks bound inside the protons and neutrons of our bodies. The universe is unfamiliar in scale, yet continuous in law. Still, continuity does not mean completeness. General relativity describes gravity with extraordinary success, while quantum theory describes matter and radiation with equal power. Inside a neutron star, both are essential. Deep inside a black hole, they may no longer fit together in a complete way. The unresolved tension is not a failure of science, but a sign that the story is unfinished. Our theories are maps drawn from experience, and every map has an edge. Dead stars gather several of those edges into one place, inviting us to search for a framework broad enough to describe matter, information, gravity, and space-time together. We may never receive every answer in the form we expect. Some interiors may remain permanently hidden behind horizons. Some phases may imitate one another so closely that no single observation can distinguish them. New discoveries may replace today's clear categories with subtler ones, revealing gradual transitions where we imagined sharp boundaries. This is common in science. Progress often makes the universe less simple before it becomes more coherent. The reward is not always certainty. Sometimes it is a more accurate understanding of what can be known, what remains uncertain, and what kind of evidence would change our minds in the years ahead. The limits themselves may carry meaning. To know that an event horizon prevents information from returning is not the same as knowing what lies beyond it, but it is still genuine knowledge about the structure of nature. To place an upper limit on a neutron star's radius or a lower limit on the pressure of its core may sound incomplete. Yet these boundaries can eliminate entire families of theories. Science often grows through such careful exclusions. A blank region on the map is not empty when its borders have been measured. It becomes a defined unknown, a place where future ideas must enter without contradicting what the universe has already revealed. So, could dead stars become stranger than black holes in the complexity of their matter? Perhaps they already are. A neutron star may contain more distinct physical phases than any other enduring object we know. It can behave as a crystal, a superfluid, a superconductor, a magnet, a relativistic clock, and a source of gravitational waves. A black hole may be stranger in another sense, because its horizon transforms the relationship between events and observers, and because its existence brings gravity into conflict with our understanding of quantum information. The question has no single winner, only two different doors into the unknown. And now, as this journey settles into silence, imagine one of those remnants turning somewhere in the dark. It may be a quiet neutron star, cooling slowly as invisible neutrinos leave its core. It may contain matter with no confirmed name, hidden beneath a crust only a few kilometers thick. Or it may have crossed the final boundary and become a black hole, carrying its history behind an event horizon, far away. Its influence continues through gravity, light, and time, here on Earth, beneath a calmer sky. We remain part of the same universe, listening to what reaches us and resting beside what we do not yet know.